Okay, I hope you enjoyed the lunch break and had many conversations. I think we go to the next session. We are already at session 3. The next topic will be presented by Tassilo Glander from Vicomtech. It's about geovisualization using WebGL.
Yeah, thanks for introducing me. So again, my name is Tassilo. I'm from Vicomtech, originally from Berlin, and now I work at Vicomtech in Spain, which is a research institute that's doing applied research for with projects of local companies. And today I'm going to present geovisualization and WebGL using WebGL, and I added a subtitle which is to reuse desktop software to do this. So I'm going to present to you a methodology to reuse existing software that you used on the desktop machines, and how to render the output of those applications in the web. I did this work together with the colleagues that you've seen here, and some words about geovisualization to start with. It means geovisualization is about visualization of spatial data. So it involves, first of all, visualize something, which means to make it understandable, to make it comprehensible. It might be data that has a spatial shape, and you just display it. But it might also be data that is abstract, and you need the, for example, the landscape metaphor to visualize it and to make it more graspable. So you can have any information visualization and just use the landscape metaphor to display it, for example. Another aspect is geo. So in this case, we are dealing with spatial data. Most of the time, that is data that's on the Earth. And as a look on the agenda tells us also, it's a booming topic. So we have, I think, 50% of all presentations today are about geovisualization, and it's been a hot topic since 10 years or so. And so it's fundamental technology for many applications, from location-based services, from car navigation systems, but also in science, to just visualize abstract data that you measure or that you simulate. So some characteristics of the geodata. Geodata is massive. So it's we have already heard some numbers today. It's terabytes or petabytes of data, just because Earth is so big, and to get a high resolution of the data, we have really high demands of the data storage. It's also heterogeneous. So we, of course, in the graphics card, everything is triangles and raster data, so textures. But to get there, we have to support lots of different file formats. Especially in the geo domain, there are several players which develop their own formats, and to come up with a geovisualization system, you have to support all these different kinds of input data. Another characteristic is that these have spatial reference systems. So if you are on the globe, everything is just nice, and you have intellectual properties. So on the one hand side, we have commercial data providers which are quite picky to let their data not get into the free, to not release their data. And if you're using them, they have the lawyers at their side which enforce this. And on the other side, you have a very strong community which delivers data, for example, through OpenStreetMap. Or I'm not aware of another one, but yeah, so we have those two directions. And to give some examples, so that's the typical globe thing. This globe visualization, in this case, it's taken from OSG Earth. OSG Earth is based on a desktop rendering middleware, OpenSceneGraph, and it adds on top of this capabilities to display spatial data, for example, as a globe, but also on a flat terrain, for example. So it includes to do this, you need to have a tile-based rendering, because you need to handle the different levels of detail, for example. Another example from the geodomain is CityGML viewer. So CityGML is an open standard for storing semantical, graphical surface data of building models or more city models, and especially in Europe, it's quite popular. For example, so it was specified by the Open Geospatial Consortium, but initiated from a German research group, and it's used, for example, in Berlin for the full virtual city model containing I don't know 300,000 buildings, I think, and it's actually used also. It's all start to getting used in the cadastre. So it's not just the 3D graphics that comes out of those models, but you can actually store extra semantical data, which also means, on the other hand, that you have another input for visualization, which you can use. In this example, you can see that through the semantics that are encoded inside of the model, you can actually do transformations based on the different data types and components inside of the model. Or another example is Amsterdam. They released their model also to the public in CityGML. Another example is oceanic flow visualization, as you can see on the right hand side. This is data that comes from the NASA, for example, which just shows the global flows of the oceans. And to visualize this, there are certain visualization techniques like this line integral convolution filtering, which you can see here in the background. But there are also other ways, for example, to use the flow lines to visualize just the way where the water goes. Okay, so these are a few examples, and now what's the status of to visualize this? So how do visualization systems look today? So we have the desktop world with the machines and the operating systems, and on top of this the drivers, of course. And then you have a middleware and abstraction layer. We've heard something about abstraction layers this morning also, and on top of this you have real applications that are for a certain purpose. Were written for a certain purpose. But this is on the desktop world, and then we have, in parallel to this, we have the browser world which now supports through WebGL also 3D applications, and we have a lot of frameworks that come out of the space right now. We've seen some great demos this morning also, and but they are quite separated, these worlds. So so some properties of WebGL, I think they are quite known, so it's a universal platform. We don't need plugins. But on the other hand, it's also a new platform. It's just 1 year old. So lots of developers have experience with C++ and OpenGL on the desktop side, and also there exists quite some code, some libraries that were written for the desktop world. So this is something of a challenge for WebGL, and also JavaScript and WebGL. Everything is readable. If you download it in the browser, you can get everything out of the data. Okay, there are some obfuscation techniques, but in the end, you can get pretty much of the code. So yeah, for geovisualization, as I said, there exists some libraries already. And also we have to take care that proprietary data is not maybe not given away as freely. So we propose a crazy idea that may be crazy for you, especially because you're embracing pretty much the WebGL, but we thought that let's take this generic subset of OpenGL that is defined by OpenGL ES, and which is also the basis for WebGL, and use this for applications that run on all those platforms by implementing an OpenGL ES driver that translates the calls, the C++ or C calls to the GL driver, and translates this into JavaScript code. So this what we win of this is that we support now everything with a single interface. And we can actually bring those C++ middleware, rendering middlewares to WebGL also. So I put here OSG, but in theory we could also support Visualization Toolkit, for example. They have a OpenGL ES port also. OSG also supports OpenGL ES, so that's our win here. Okay. So yeah, the idea is to exploit the similarities between the API and create the driver. So to give another overview, usually on the desktop you would just have this application and it would run with a GL driver and local would translate the calls locally to the GPU, and we just replace the driver by our proxy driver, which is connected to a web application server, and if the client opens a URL, the application is run on the server, but just the OpenGL calls are tracked and sent over to the browser and executed at the browser on the fly. So how does it work? This is based on the Web Toolkit, which is from a Belgium company, MWeb. They provide a software library that is similar to Java server pages or PHP, where you have on the server side you create the web page on the fly, but they do it with C++, and it's oriented on the Qt library for the desktop also, and yeah, it provides a web server, and it also has they call a WGL widget, where you can actually call functions that are related to the WebGL functions. So this is an example. If you call depth range in the C++ program, it will generate it will generate the JavaScript code by putting those strings into the JavaScript stream, which is then sent to the client, to the browser. Okay, what we add on top of this is we create the GL driver, the GLES driver, and provide the includes for this, so we can binary link our OpenGL desktop middleware, which has to support OpenGL to this, and we also have to provide to provide some workarounds around some limitations, because, for example, client-side arrays that are supported by OpenGLES are not supported by WebGL, so we need to create buffers for that. Okay, what we also do is we split the calls, the commands of the OpenGLES into init calls, initialization calls, and paint calls, because you don't want to create the buffers inside of the rendering loop, but you want to do this in an initialization stage. And the same for the paint stage. In the paint stage, we just want to do the draw calls to set attributes and uniforms, for example, and apply shaders. So the workflow would be like this. We start the server. At some other point in time, the client queries the URL, and the application is started on the server. The 3D scene is created, and we do. So usually those middleware frameworks have some central render call, like for example in OpenScene Graph it's called frame, which does all the rendering, and we enable in the proxy we switch between the init filtering stage and the paint filtering stage. So in init we just send the calls to OpenGL yes, that are related with buffer creation and everything to the client, and in the paint call we just send the calls that are related with the paint, the actual render loop. So that means on the server we just run twice the scene traversal, and then everything else is done on the client. First the initialization function is called and executed, and then we have the rendering loop, and so we get the live images there. And if we move if there's a certain event, we have to update the client-side data. For example, to load a new level of detail, that means we have to create new JavaScript and apply this. Okay. Yeah, we have some. So the browser essentially is a very thin client. It has a very thin JavaScript client. It only is capable of loading those simple functions, init and paint, and it sets off a number of draw calls, and then there's also some client-side interaction, so that you can get the mouse and interaction, and you can move around in the scene without getting back to the server. Okay, a few words about how it's working. So we need to set up some helper structures to map between the client-side GL objects and the server-side GL objects. we need to work around client-side arrays. And for shaders, we eventually have to provide a default shader or to provide some mechanisms to automatically transform OpenGL 2 shaders to OpenGL ES 2 shaders. Okay, so some results of it. So it's still quite in the early stages, but we were able to run a few OSG example programs. So if you know OpenSceneGraph, you're maybe familiar with those examples. So we have support for the different primitives. We can use with the help of this the standard shapes that are provided by OpenSceneGraph. And for example, we did a test with lighting as well. Actually, we started with the learning WebGL tutorials, implemented them with Witty, so that was quite cool to start working with this. And then we also did another example with CityGML. So it's a good use case for this methodology because CityGML is quite complex standard, and there exists a library for C++. Which creates just the 3D scene, and we, with the help of this and our framework, we were able to just show it in the client, in the browser. Yeah. So the issues about here is also that CityGML has everything specified. For example, they have walls, they have windows, they have the roof. Everything is different geometries, so you do need some optimization algorithm to batch files and to make it more efficient, and OpenSceneGraph just provides this by default. So that's another advantage of reusing this this middleware. Another good example is the streamlined oceanic flow visualization, because it is this implementation is based on CUDA. And so far, we don't have a WebGL. I don't know if it has arrived yet, but we don't have CUDA in the browser. So this is a way to provide clients or provide browsers with a visualization that comes out of a computation that is being done on the server, and only the resulting geometry is sent to the client. So in this project, there are line strings created, and the shape of the line strings they follow the flow, and this was created in CUDA because it involves some hierarchical tracing techniques of the flow inside of the vector field, and the result is just the 3D line strings that are just sent to the client. So we don't need to do this on the client. The server computes it and sends just the visualization to the client. Okay, some problems with this is so the major problem is dynamic scenes. So usually if you do some computation in the JavaScript, you have a short way from the CPU to the GPU. But in this case, with our approach, the way between the CPU and the GPU is basically the internet, the network. So we have problems if the scene needs to be updated really often. In geovisualization, you usually have big models, but you have not so often updates. Just for example, if you zoom in, you have updates because of the new level of detail models that are being streamed in. Some tests. So we just animated this triangle, just rotating. It's just sending a single matrix. We had have quite some overhead of data and also of time to send this to the client. Maybe you guys have some ideas how to improve this. I already had some nice talks about it in the lunch break. Okay, some conclusions. This methodology brings WebGL-based geovisualization to C++ systems, to the C++ world. So our argument is that we should continue to use those middleware software that are available for the desktop, and it enables also to reuse experience that developers have with C++. Feasibility in general, the performance is good. If we need lots of updates, we have a problem. We have no cutting edge features that we have on the desktop for GLES. And so it's basically it's not maybe not the best thing to choose for if you're doing a game, but for scientific visualization it has some good points. Okay, so I'm ready for questions, and thank you for your attention.
We do have time for questions. Okay, there are some questions. Let me start here.
Roughly how much data is transferred from the server to the client for a single frame?
In which case of the example?
Or give an example of, I don't know, the CityGML, for example.
For the CityGML, you just have, I mean, basically what the server does is it creates the geometry and the texture, and everything is sent to the client. So it's like loading a file. So there's just the initialization loading time, which is about 10 seconds. I'm not sure about the data size, but yeah, I mean, it depends on the model. Basically, you have to transfer all the texture data and all the geometry at once.
Okay, next question.
Very interesting. I don't have a question, just a remark. It reminds me a bit of the architecture of the former OpenGL systems I heard in computer science or in graphics lectures, where you had a client and a graphics server, and you generated a stream of OpenGL commands that were parsed by the server and then generated an image. And then what you are doing is that you're actually putting an intermediate step by generating HTML and WebGL output, which then again will generate the stream of OpenGL commands. So that's a really interesting approach.
Yeah, you're right. It's quite similar to those old. I don't know. VNC has also I think application for this. But you're right. We have a quite thick abstraction layer in the middle of creating string on the fly for all the buffers that are out there in the beginning, binary, and have to be sent to the client, and then again they get binary data. So I had some nice talks today about how to maybe speed this up by just using binary data to transfer this.
Okay, we have one last question.
Well, that was basically my question. So my question was, do you compress the data set using gzip?
Yeah, I mean, just the standard. We just in Witty you can just enable compression, and then the standard compression is used. But again, I mean, it's a string, and we are sending strings over the network. So I think a big optimization potential lies in using binary data and maybe compress the binary data. Okay, thanks.
Okay, thank you again.